All right, here's the lesson on nonlinear regressions. A regression is the ability to take a table of values of some sort and to find a math equation that closely matches the table of values. So then you could use that model to predict something in the future. That's the idea of a regression. So this is information about the past, and we have an equation that matches up to it, and then we can use that equation to answer a question in the future to predict what's happening. So you might have done this before with a line, where you find the line of best fit and then use a linear model to predict the future. Here are different types of models that are not linear. So one is an exponential, and likely when we're talking an exponential here, we're probably only talking the first quadrant. Power function is similar. Notice a power function, at least if you draw it as a parent, would start at the origin, not the exponential. If you want the other one, it could be like this. But really, we're looking again at the right end behavior. A logistic one has a cap to it. And so it increases and then it levels off. So it has kind of that look to it, where it increases and then levels off. A logarithmic curve has this feel to it. So here are different types of models that can model growth or decay. Now, it's going to be a Desmos lesson, so we are definitely going to need Desmos for every question when we do this. The population of a city from 1995 to 2000 is shown to the left. So we have a table of values, and it tells you the type of regression to use. So it says use an exponential regression. So I want you to go to Desmos. I'm going to do the same thing. And let's just start from the beginning. I already have some things I put in here. I'm going to move my head over here. First thing I want you to do is press the plus sign and table. And we're going to put the table into Desmos. Now, for the first one, I'm not going to use 1995. Instead, I'm going to go 0, 1, 2, 3, 4, 5, and recognize 0 represents the first year that I'm looking at it. So we have 54.5, 55.6. This is what takes the longest, is to put this into Desmos. And then we're going to let Desmos do the regression for us. And I'm going to teach you how to do that. So double check, make sure I typed it in correctly. I want you to notice, if you look here, these are the points I just did. And so we're going to make an exponential curve out of this, where it's going to curve up and it's going to match these points. How I'm going to do that is I'm going to type in, notice we have a table that's x1 and y1. So we're going to type y1, and then we need this symbol. Now, it's not on the Desmos keyboard. So if you click on the Desmos keyboard, it's not here. It's actually on your keyboard. Now, on my actual keyboard, it's on the top left. And I go shift and that. So I wonder if you can find where that is. Kind of looks like a mustache. And then I'm going to type in an exponential, which is a times b. I do need the keyboard for the exponent. And then in the exponent, I'm going to put x1. So there is a exponential model. Notice it actually graphed it here for me. And notice how the line goes through the green points to create that exponential curve. I'm not going to do a stats lesson with you, but R squared is a statistics term. What you do need to know about R squared is that the closer that is to positive 1, the better the model is. So 0.9926 is really close to positive 1, which makes it a really good model for what we're doing. So A is 54.661. So I'm going to write that down. So A again is 54.661. And then the base B is 1.01357. And we're going to write that to the exponent x. So now we have a model that goes through those points. So there's my equation. I'll let Desmos do it. And then it says, find the year in which the population will reach 80,000. So x is the year. I'm solving for x. So f at x is 80,000. But in our table, These were all thousands, so I'm just going to go 80. So this is the equation I'm going to solve, and I'm going to show you how through Desmos we will solve it most accurately. So there's the setup, and then we're going to use Desmos to be able to do this part to actually solve for x for us. So come back to Desmos, and then another box, type in the information. So 80 is the second column. It's the population, it's the y coordinate. So we're going to go y equals 80, and we're just going to type it in, and what we're looking for is where they intersect, 80 and the curve, and then what's the answer where they intersect. So that's actually the solution to the equation, and using a graph to solve an equation. Pretty powerful, right? So we're going to round it to 28. Then I can then answer the question. So remember we said this was 0. So 28 years later, it's going to be 80,000. So what's 28 years later? So that's 5 and 23. So it'd be 2023. That's what it would be in terms of years. So in the year 2023, the population will be 80,000. All right. So in the year 2023, the population will be 80,000. There it is. That's what we're doing. So in the first questions, they tell you what type of regression to use. And the last two, we have to figure out which one is the best one. All right, the next one's called a power regression. But you see our table of values. Step 1 is to put that into Desmos. So let's practice again. So I'm going to clear this, and then I'm going to click plus, and then the table again. So plus and table. And then I'm going to put in the information I see, which is 0.5, 0.6, what isn't 0.6, 0.7, oops, come on now, 0.7, 4.5, 11, 65, 110, and 155. And then the y values that go with it. And now, it's good for me to understand the story that's talking about, so we'll talk about what the story is about. So in this case, the story is about different weights of animals. That's the first column. And then the second column is their beats per minute. Their pulse rate per minute. So a really, really small animal, like a hummingbird or something, the heart rate is like goes really fast. The bigger the animal, it slows down. So you can see that. So here's that model of like something's really light. The heartbeat is really fast compared to something heavier, and the heartbeat beats a little bit faster. So that's on my graph. You can't see it. If I zoom out enough, I would probably find them. So there they are. So I can see the points that I have here. I want to make a power regression with this. So if I want to make a power regression, I'm going to go Y1 and then that symbol, right? That wavy mustache looking thing. A power regression is A times X1 to the power of B. And then when you type that in, you can see Desmos then correlates it. It's 0.95. So it's not as strong a correlation as the other one, but you can see it definitely goes through some green points. There's a couple points that are a little bit off. Part of the reason is the last data point, the heartbeat went up, even though the weight went. Heartbeat didn't keep going down for the last one. But anyways, there's something that models the points that we have. I'm going to write it down. So 0.953 is still close to 1. It's just not as good as the one we had before. So I'm going to write down f at x equals A is 303.597. The base is x, and the exponent is negative 0.309157. So I have a power function now that I can use. Let's go back here. So there's my equation. And x represents the body weight, and then the y coordinate represents the pulse or beats per minute. Estimate the pulse rate of a 225-pound animal. That sounds like me. So 225, make it equal to that. And then what should my pulse rate be? So let's solve this. Equal to 225. Again, we're going to let Desmos do this work. So we're going to write down y equals 225. And then we're looking for the point of intersection between that and the red. Oh, what did I do wrong? So the weight, sorry, it's F at 225. So the weight is 225. So that's the X column. So here's what we're going to do. Totally different. So we have an equation. So now we're actually, this is what, it's not going to be y equals because it's the first column. Weight is the first, is the X. So type in X equals, and then where they intersect is the answer. So that can work for a substitution question, an evaluation, solving an equation. You're just looking for the point of intersection. And then this tells you the beats. So approximately that's about 57. And then we write the answer down. So the answer is 57. So the pulse rate of a 225-pound animal should be 57 beats per minute. All right, let's look at number 3. The table to the left shows the temperature each minute after an oven is set. So you set the oven to heat up, and in the first minute the temperature is 77, and then it keeps warming up every minute. So can you model this? And we're going to model it with a logistic regression, because there'll eventually be a cap on the temperature, right, at 400 degrees or whatever, and then so it increases and then levels off. So make sure that when we type it in, use this as a reference to know how to type it in. So let's go back to Desmos. We're going to X out of what we've already done. We need a new table. So let's do a new table. So in the first minute, the temperature is 77. In the second minute, the temperature is 98. In the third minute, the temperature is 124. In the fourth minute, it is 152. Oops. In the fifth minute, it's up to 185. All right, and then you can actually see the temperature rising right there. All right, so what is a logistic model? What is it going to look like? So I'm following what's on the page. So I'm going to go y1 equals, and then a divide sign. In the numerator is c. In the denominator is 1 plus a, and then e. And then the exponent on e is negative bx. Now we're going to call that x, x1. And as soon as you have y1 and x1, oh, what just happened? Where did our points go? So c over 1 plus, our whole table just went away. So let's try it again. Let's see if we can do the table again. Why did my table disappear? I don't know why my table disappeared. So let's do the table again. The table is 1 and 77. It is 2 and 98. Oops. It is 3 and 124. It is 4 and 152. And it is 5 and 185. All right. So, and now we have this here. I don't want to slide it. Let me get rid of this. Feels like my computer's going slow. All right, so let's try it again. So this time it's y2 and x2. So I'm going to go y2, and then I'm going to go this. Did I do that sign? Maybe that was it. Maybe I didn't do the similar sign. That could be it. I forget. And then we're going to type this in, which was c over 1 plus ae to the exponent. That was the issue, wasn't it? To the exponent negative bx. We'll solve this, and it's x2 with our data. All right. So there it is. So there you see a logistic growth model. I wonder, intrigued, like, see where it caps off here? So it grows, and then it caps off. Now C is the cap. So C is 478. So that's the cap of the temperature, according to this model. And then the question is, so I'm going to write that down. So f at x equals, so C is 478. Well, I'll just round. 1 plus A, which is like 7. E is a number you know. And then B is like 0.3. So negative 0.3 x. So there's a logistic growth model right there. So now we have a model. And then it says, how estimate the time. So we're looking for time. So we're looking for x when the temperature is 425. So we're going to make it, here, I'll just do it on this side. We're going to make it equal to 425 and solve for x using Desmos. So how will I do that again? So open up a third box here. And it's the second column. So it's y equals 425 degrees. And then the first gray area is the y-intercept. I don't want that. I want to know where they intersect. So where do these intersect, the logistic growth curve and 425? And that tells you the time. So 13.546. And we have our answer. So I don't know if you've ever solved an equation using a graphing calculator, but it's pretty powerful and simple to do. All right, let's write a simple sentence. So the question again is, estimate the time it'll take the oven to reach. So after 13.546 minutes, the oven should reach 425 degrees. Done. All right, turn the page. How are we liking it so far? Here's the second page. Where's the second page? Here's the second page. All right. So let's try this again. This time we're going to use a logarithmic regression. So the story here is the X column is years. So this is the first 8 years. And it's to estimate the enrollment. So the first year the college was open, and then the 8th year. And then we're going to use that to answer the 15th year that it's open. So step one is to understand the story and then put it in. So in year 1, 867 students were in college and then kept going on from there. So let's go back to Desmos. Let's put in our table. Make sure I don't make a mistake like I did last time. We learn from our mistakes, right? So here's the table again. So we're going to put in year 1. There's 867 students. Year 2, 1753. 3, 2,272. 4, 2,639. 5, 2,925. 6, 3,158. 7, 3,355. 8, 3,526. All right. So if I want to look at that on the graph, I'm just going to zoom out here so you see the points. It's kind of nice to see the points, and then once you do the regression, you can see if how they match or don't match in terms of it. The scale is a little bit tricky because it's 1, 2, 3, 4, 5. So that's why if I did this, you would see it better. So if I go and I change the X, so it's 0, and my computer's like being silly. So like if I go from 0 to 10, no. So if you do that, you can see it better. So from 0 to 10, you can see those points. We're trying to find a regression that would, match those points. So it says use a logarithmic one. So look off that first page. Make sure you know the form of a logarithmic, and it's a natural log. So we're going to go y1 and then that similar sign, and then a plus b, and then it's ln x1. And then can you see how great, look at that. I mean, it's like matches it. In fact, when it says, when you look at it, it's like, what does r squared equal? It equals +1. That like is a perfect, it's a perfect logarithmic increase, like perfect. And so when r squares equals 1, it matches perfectly. So for that data, it matches perfectly to a logarithmic one. All right, so let's going to write it down. So f at x equals, a is 800, we'll call it 867, plus b, we'll call it 1,279 ln x. So there's our equation. So all based these numbers from Desmos doing the hard work. And then the question is, estimate the enrollment in its 15th year. So I want to do that. Now, one way you can do it, Desmos, for this one, is 15. That represents the x coordinate, or the first column. So if I type in x equals 15, x equals 15, and then move the graph over to 15, like where do they intersect will give you the answer. So there's different ways you could do it, but that's definitely one way you can get an answer. So 15, how many students? Round it, so it's 4,330. So the question is, estimate the enrollment. So in the 15th year, the enrollment should be 4,330. And this is what it looks like. All right, number 5. Once a new lake was filled, it was stocked with catfish. The table to the left shows the expected population of catfish in the lake each month thereafter. You'll use logistic regression to write an equation to model the data. So again, let's start with Desmos and put that table in. So there's a good start. So erase what we had before, press table. Let's do a fresh table. So the first month, there's 140 catfish. The second month, there's 162. The third month, 187. The fourth month, 215. Make sure I'm reading the right question. 141, there it is. Fifth month, 248. So, and again, if you want to see, you can see here, and so we're looking for data that's going to go right through that and match those points. So if we use a logistic growth model, again, it's going to be y1 and then similar, do a fraction. The numerator, I'm just following the page. So I'm following the model of a logistic, which is c and then 1 plus a e to the exponent negative b x1. So there it is. And again, can you see how it like r squared equals 1? So that means like it matches it perfectly. So that's a great model. So let's write it down. So it's f at x equals c is 3,622. That's the maximum number of catfish that would be in the lake. 1 plus a is like 29. E to the exponent negative 0.2, 0.15 x. So there is my model. Desmos helps me do that regression. So now I have a great model where I could do anything in terms of up to like, so it says in 8 months after, estimate in 8 months, I could do 12 months, 100 months. I could estimate 300 fish, 400 fish in what month, and so on. So now, once I have an equation, I can answer any question connected to the story now. So that's why it's powerful. So the question is 8 months. So that means we're going to plug in 8. But instead of substituting 8 in, we're just going to go x equals 8 and then look off the graph. So if I go x equals 8, and then I move the graph so I can see the value of 8 on the x right there. Tap on the point of intersection. So at 8, how many fish? And it's 375. And you can see the growth of the fish in there, and then eventually, because it's logistic, it eventually will level off at a certain number. So see how it kind of grows and then it levels off. And we know it levels off at 3,622. I mean, look at this scale here. All right. If I click home, it goes back to something different. All right, let's write a sentence. So the question is, after 8 months, 375 catfish should be in the lake. All right, so now 6 and 7. You have to choose the model. And what we're looking for is r. It says r between -1 and 1, but when you square r, it's always a positive number, and we're looking for the answer closest to +1 for r squared. So we have 4 models to look for. So we're going to do this, and then we're going to look and type in with Desmos each model. Whichever answer is closest to +1 is the best model. So let's just start and understand the story. So the average price of gas. So this is 2001, and then 2, 3, 4, 5, and then you can see the price of gas from 2001, and then it says find the year in which the price of gas will reach $3.25. Okay. So let's type this in, knowing that 1 is 2001. And then we just have some work to do with the different regression models, and we just want to look at each one and see which one is closest to +1. And if there's more than one, maybe, well, we'll see when that happens. So, table, and then put in 2001, it was $1.38. In year 2, it was $1.65. In year 3, it was $1.95. Year 4, 2004, $2.32. And then in year 5, 2005 was $2.95. And then we're going to take that data and we'll just go one model at a time. So the first model is exponential. So it's y1 and then similar. And it's a, b to the exponent x1. So we'll look at that first and go, okay, so 0.993. That's pretty good. So let's try another one. y1 similar. The power one would be a x1 to the exponent b. 0.91, that's worse. So we're looking for the one closest to positive 1. So far, this one is a better one. I'm just going to X it out. So whatever one's winning, I'm going to keep. If it loses, I'm going to get rid of it. So it lost. So the next one, Y1 is a logistic one. So it's C, and then in the denominator is 1 plus AE. I forget the exact model for this one too sometimes. And then on E is negative BX1. This one, it's 0.9988. Wow, that one's even better. So we're looking for the one closest. I'm checking the answer key to see if it agrees with me. Oops, it didn't even put it in right. Let's see if I can put it in right. So right now the logistic one looks really good. So for this one, I'm looking at the R squared. So 0.993, 0.998. So this one's better, right? Making sure. Yes. So get rid of the loser. So now we have one more model to look at to see if it's better or not. That's the logarithmic one, or a natural log. So that one is A plus B, and then it's ln x1. Oh no, what? Oh, please let me go back. What just happened? Oh, I know what I did. That equal sign again. Let's go back. I did it again. That's what I did last time. I just forgot. So x1, there we go. All good. And you can see this is actually the worst model, is the logarithmic one, 0.846. So we looked at each one. Which one gave me the best R squared score? The one closest to positive 1. And that's what I'm going to use. So I'm using that one. X is the years, and the F at X is the price of gas. C is negative 0.82. Six. And then C, that was C. B, A. A is negative 1.68, and then E, and then 0.05, and negative. All right, so I just wrote down the numbers down, kind of rounded them. This is what it looks like. I don't kind of look at it because it looks like the numerator, it kind of flipped something around here on me. So because both are negative. Anyways, if I actually look at the graph, it looks actually okay. So I can see that. And then the question is, find the year in which gas is $3.25. So that's the Y value. So what year would it be $3.25? That's here. And so you could see that $3.25 right there in year 5. A little more than year 5, between year 5 and year 6. Will be $3.25. All right, let me show you my work again. So between year 5 and 6, the price of gas will be $3.25. It's an interesting model as it just keeps going up and up and up. It's not like a normal logistic one where, in terms of it. All right. One more left. Can you look at the last one? Let's look at the last story. It's just interesting because A, as it goes, it's kind of a funky model. But that's okay. So again, we're trying to find the one that matches closest to what we're doing. That gives us the best R score. All right, last one here is number 7. And the table for number 7, it's the wingspan in feet compared to the Y. So the weight in pounds of 5 birds determine whether an exponential or power function would best fit it. So, determine whether a logarithmic or an exponential function would be best. Well, I'm just looking at all the models to see which one would be the best model for what I'm doing. And then estimate the weight of a bird with a wingspan. So this is the weight of the bird, and the wingspan is here on the right. So X, table below shows X. Okay, so X is the wingspan, and Y is the weight of the bird. All right, let's go from there. So the weight compared to the wingspan. So let's put that in. Make sure I know what each variable represents. So let's get rid of these. So let's do a table. So for this one, we have 1.7, the wingspan, and the weight is 0.21. 2.4 is the wingspan, the weight is 0.56. 3.5 is the wingspan, and 1.6. 7.2, and 12, and 9.3, and 24.7. All right, next, let's look at first an exponential. Oops. Do the 1, there it is. Oh, it didn't. Oh, I did that again, didn't I? So, let's get that data back in there. Poor thing here. There it is. All right, so now we have it. So R squared is 0.9905. If I do a power, oh, I did it again. I have to stop doing that. So, oops, let's go forward. There's the data. Let's do this properly. Don't let me keep making that mistake. All right, now we got it. And then I look to see which one is a better R squared. So you can already tell that R squared equals 1. I mean, it doesn't get better than that, R squared equaling 1. So I don't need to try any other models. That's perfect. So I'm going to be done with that model. I'm not going to try any more models because I just found the perfect one. So it's a power one where A is 0.05. The exponent x and the exponent is 2.8. So this is what it looks like. And then the question is, estimate the weight of a bird with a wingspan of 5 feet. So x is 5, and what would the weight be in terms of that? So, I mean, it's going to be in between 1 and 12, right? We can see that already. So x is equal to 5. So then what's the wingspan? Let's put this back to normal again. There it is. And so at 5, I get the answer 4.3 being the weight. All right. So now write a good sentence. So a bird that weighs 4.3 pounds should have a wingspan of, what are we looking at? 5 feet. Done. So a bird that weighs 4.3 pounds should have a wingspan of 5 feet. Hey, that's it. So these were all nonlinear regressions. And we're using Desmos and doing a table of values, and we're modeling with Desmos and finding the model that gives me the r squared closest to positive 1. And then we're using it to answer a question in there. So Mr. G Math, over and out. I'm proud of you, and I will see you next time. Till next.